So in our last video, we touched upon the idea of the difference between theoretical and experimental probabilities and relative frequencies, as well as how to find probabilities with their desired outcomes over the total number of outcomes as a fraction. So now we're going to extend that a little bit further and use that in context for some different problems. Let's go ahead and jump right in. Let's do this. Boom. So a fair coin is flipped 14 times. How many times is it going to be heads? Well, you know that heads is the one desired outcome out of 2 total, and I'm doing this 14 times, so that's going to give me an answer of 7. So 7 times I would expect to see heads. I might not get 7 exactly, but that's what I would expect. So now let's say that statistical data is built up over 5 years that shows the probability of a student being absent at school is 0.05 or 5%. There's 531 students in the school. Predict the number of students you expect to be absent on any given day. Well, if my probability is 0.05, I'm going to multiply that by my population size or my sample size, which is 531. And what I'm going to get here is, and you'll get about 26 or 27 once you round. You'll get in the middle of those. So what that means is that I can expect on any given day for there to be about 26 or 27 students absent from the school because there's a 5% chance, and 5% of 531, rounding up or down, would be 26 or 27. So now state the assumption supporting your answer for part B. Well, I'm assuming that there's equal likelihood for the kids to be sick on any given day. I'm not taking it like flu season into account. I'm not taking traveling or holidays or anything like that. That might cause a spike because typically illnesses and viruses and stuff like that, they follow, it's not linear and it's not flat in terms of like contingency, right? Cyclical. There's spikes and things like that. So like that's one thing that doesn't take into consideration. Again, there's multiple ways to answer this, but it'd be something along those lines that the IB would be looking for. So now let's take a look at this example down here. We have a much more intimidating looking table. However, if we read the context, it's really not that bad. So we know that the coastal town is going to carry out a survey of tourists in July 2018. So there's different types of accommodation as well as different age brackets. Now I'm going to go ahead and give you a little spoiler here that the typical way that you want to solve these is by extending these down and finding the total for your columns and your rows, because that is how you can kind of easily figure out which probabilities you are going to need to consider. So let's go and do this, this, and this. Okay, so what I want to do is I now want to add up the different totals for my age groups and then my different accommodation types, and I'll show you why in a second. So we have, in the 18 to 30 group, we have 67 people in a hotel, 81 in a camper van, 125 in the tent, and 32 in the apartment. So that means we're going to have a grand total of 305. If we repeat the same process, we'll have this at 529, we'll have this at 286, and then we'll have this at 210. So go ahead and try out on your own the ones for hotels, camper vans, tents, and apartments and see if it matches up with what I have here. Because what I'm going to get is that down here for hotels is 370, right here is 419, right here is 247, and right here is 294, giving me a grand total. And again, no matter which way you're going, whether it be adding up the rows or adding up the columns, you're going to get to the same number because you should have the same exact total given your sample size, and that's going to be 1330. Okay, 1330. So now a tourist is choosing at random to receive a promotional offer. What age group are they most likely to belong to? So I don't actually have to do any math here. I just have to think, okay, which age group has the largest representation in the sample? Well, I have 305 18 to 30-year-olds, 529 31 to 50-year-olds, and 286 51 to 70-year-olds, and then I have 210 elderly folks above 70. So clearly my answer is the 31 to 50 age group. Okay, because I have 529 people. So let's find the probability that a tourist chosen belongs to this age group. Well, again, quite easy. I have 529 desired that I'm looking for out of my 1330 total. And what is that going to equal as a decimal? That is going to be, let me check my work. That is going to be 0.398, and I should really use the squiggly equals here to be more exact. About 0.398, which means that it's almost 40% of the population, that age group, 31 to 50. And now in part C, 16,000 tourists are predicted to visit the town. However, the hotels only have a capacity for 5,000 total people. Are we going to have enough? Well, our probability states that we had 529 out of 1330 the year prior. But now I'm going to have 16,000 tourists. That's going to be my new population size. So what does this mean? This is going to be the likelihood of the number of people out of 16,000 to stay in a hotel. And what I'll find is that my answer is going to be about 4,451, meaning that yes, I do indeed have capacity. So that's one way that you can use these probability models to kind of extrapolate and apply to a larger population size to figure out what your expected values might be, whether that be number of coins, the number on a die, or even something in terms of a hotel and accommodation types. So I hope that spread a little bit of light into how we can use these probabilities, and I'll see you all in the next one.